Hello, everyone. Thank you for being here. As said, I'm Yolan Romailler. I'm from Switzerland, not to be mixed with Sweden. So we got the chocolate and the cheese fondue, and they got IKEA and yeah, even more snow than we do. I love playing CTFs and also board games, and I love to go to conferences. And you should definitely submit talks to conferences if you want to be sure to go to a conference, because then you have to, right? So here I am. So today we'll be talking about randomness. So what is randomness and what kind of randomness there is. Then we'll see why we need randomness, what kind of problems we have with randomness, and in practice, how to avoid these problems. So full disclosure, I like to work with math and cryptography. So it will be mostly about using randomness in a cryptographic context. It won't be about using randomness for simulation or data sciences. So what is randomness? We can look it up, right? And according to the Cambridge Dictionary, randomness is the quality of being random. Truly amazing, great. So thankfully they refine it a little bit, and they say it's a quality of being random, happening, done, or chosen by chance rather than according to a plan. However, that's not very helpful for the way we see randomness in computer sciences. Other definitions capture the notion a bit better, in my opinion. So, according to the Oxford Language definition, it's the quality or state of lacking a pattern or principle of organization, unpredictability. And that's a very important word we'll need to remember later on. So, what is random? Is that random? Like, if we look at that first string, doesn't seem too random, right? Nah. How about the second one? Mm, looks better, probably random. How about the third one? Definitely not random. Fourth one looks random, but actually isn't. It's just 1, 2, 3, 4, 5, 6, 7, 8, A, B in X. And the last one here also doesn't look random, right? However, all of them have the exact same probability of being picked at random by a proper random generator. So they could actually have been generated at random. It's just they don't feel random, right? And that means we have a kind of intuition of what random means. And that intuition is actually linked to something we like to call the Kolmogorov complexity, which is basically how much you can compress a string. So if a string is very easy to compress, like the all one string, you can say it's all ones, then it doesn't feel random. But if a string is really properly random, since each bit has a 50-50 probability of being 0 or 1, it's supposedly the worst case scenario for a compression algorithm, and so it would be difficult to compress. And that's how we get that intuition of what is random and what is not. So let's go back to the start and the title of my talk. So what is randomness? I like to say there are different kinds of randomness. So the first one, the one we're most used to, would be secret randomness. The next one would be obviously public randomness. And there are a few extra ones we'll see later. So first things first, secret randomness is whenever you need your random value to stay secret. That's typically the case for your PGP key, your SSH key, or any cryptographic key you're generating on your machine. And actually, you might not realize it, but every day when you connect to websites, you're generating a lot of random values because you're using ephemeral keys to establish ephemeral diffie-Hellman handshakes when you use TLS, and so on and so on. So that's probably the most used randomness ever. But then there is also that notion I said of public randomness, and it's basically just a value that is meant to be public. You can think of, lotteries or any value you pick at random and you will show on stage. Like tomorrow this afternoon we'll be doing a draw for the raffle. They could have used some kind of public randomness scheme to draw the winning number as well, right? So we usually want public randomness for reproducibility. So in data sciences, in simulations, and so on, if you do a Monte Carlo simulation, you might need some kind of seed and be able, and that could be public because you want people to try it out as well and so on, but also for auditability. This brings us to an important distinction. Public randomness should never be used for as a secret value. Like if something is public, anybody can look it up and try generating keys with it, and it's a very bad idea to use public randomness as a secret value. So next, we have this notion of verifiable randomness, because if you have a public random value, anybody can look it up, but they might not be sure it's actually random. How do they know it's random, So we need a way to verify a public random value is actually random. So when they do lotteries, they would draw, the numbers out of this huge bowl, and you can see them doing so, and you trust they're, doing it properly and everything. When we work with computers, it's a bit more difficult to get verifiable public randomness. And so, but we still need it if we want to run a lottery, right? Because if my good friend is winning the lottery, everybody will be like, oh, you cheated, and so on. So if we want to be off the hook and be able to provide public random values in a way that will make people comfortable with it, we probably also need to think about how people could verify we've been honest. Next, we have the notion of distributed randomness. So we've seen yesterday distributed systems are complicated, and people might be asking themselves, should I be doing or should I not be doing distributed systems and so on? Well, when you are working with a distributed system or you need to draw some kind of random values, it can be very difficult to ensure your randomness is good. And it's especially true for blockchains. Like if you look at Ethereum and the smart contracts if they do a lotteries, or miners could be trying to grind the random value to their advantage. People could be trying to do front running, like watching the winning value be generated and submitting a transaction just in time to win the lottery and so on. So it's quite difficult topic to look at randomness for distributed systems. So we've seen what kind of randomness there are out there, but why do we need them? I already hinted at most usage, but mostly secret randomness is very useful for cryptography in general. So if you look at most, protocols, we have either secret keys, nonces, so number used only once, or initialization vectors that very often need to be secret or at least random. We have leader election for proof of stake, for example, needs to be done randomly, but can be done in a public, verifiable way. If you look at Diffie-Hellman, I already said so on, so on. So you use randomness a lot in cryptography, but you also use it for other things like medical trials or jury selection, or we talked about fuzzing and chaos testing, or and so on. These are things where you will need random values as well, and that's very, very, very useful. But why do we need randomness, right? Why would we need, for example, public verifiable randomness? Well, maybe you've seen at so the IRS has picked at random both the FBI director and his deputy, completely random, for a very special kind of audit program. That doesn't feel random, right, when you see that kind of things. Or maybe you've seen Bitcoin reusing the same random number to generate signatures, which led to compromise in 2013. Or maybe you've seen the PS3 hack, where Sony was reusing the same value for their ECDSA signatures as well, which led to a full, which led to being able to sign firmwares instead of Sony. So definitely we need to be very careful when we do randomness in general. And the problems with randomness is it's quite tricky, because we need randomness to be both unpredictable and bias resistant. So what does that mean? Unpredictable basically means it's not possible to predict the next random value, even if you've seen a previous one, because if you can predict the next value, you could be cheating for games or gambling or lotteries and so on. But also it could be a big problem for your system, whatever system it is that you're developing, because then it would not feel fair. If people can predict the next values, the fairness is not guaranteed. And in general, if you can predict the secret key, well, it's not secret anymore, right? Next, we have the notion of unbiased. Why do we need randomness to be unbiased is a bit more tricky. So for cryptographic schemes, it's very important because there are some schemes, like most signature schemes that are used nowadays, that are very, very vulnerable to even a single bit bias. Like you have a 256-bit string generated at random. If there is one bit that is biased, it can lead to a full key recovery attack, provided you can see enough signatures. And that's like the worst case scenario for any cryptographic scheme. And in general, if you're, creating a game or doing anything like that, if you have a biased source of randomness, it might not be fair, or it might lead to weird behavior of your system. As well, if you do simulations, recently there were some people ranting on Twitter about the fact that if you use Monte Carlo algorithm with a bad source of randomness, you won't get good results. Well, no surprise. So you remember maybe I talked about the fact Bitcoin had a problem in 2013 where some software was reusing the same random numbers. Well, with the bias randomness, it's the same thing. There was a paper in 2019 that found out that all the wallets on the Bitcoin, on Ethereum, on a couple other blockchains that were using bias randomness had been emptied already. So you might want to be extra careful whenever you deal with random numbers and cryptocurrencies, but also cryptography in general. So in practice, because we're at a Go conference, we want to see, we can use randomness, right? So in practice, do we get a random byte in Go? Well, the answer should be fairly easy. We use the crypto/rand package. We create a new buffer of size 1. We do a rand read from the buffer, and then we get a random byte. And the nice thing is the crypto rand package is abstracting all the underlying operating system complexities that might be happening. So we don't need to care about, dev random, dev urandom, all of these. And behind the scene, Go is doing things well because it's using the syscall. Like on Unix, it would be using get random properly and everything. Somehow on Plan 9, it's creating a pseudo random generator using AES. I don't know the reasons. Probably the dev urandom was too slow. But who's using Plan 9 nowadays anyway? So how do you get a random integer that is smaller than 107? That's a more complicated question, because the package that is providing a nice API to do so would be math_rand, because you can just do a rand int n 107 and you would get an integer in that range. Sadly, math_rand is not secure at all. It is not meant to provide a value that is not predictable, and it's seeded, but regardless of how you seed it, it's not meant to be secure. So you cannot say, I've taken math_rand, but I've seeded it with the crypto run package, so I'm fine. No, not at all. So never use math_rand if you're doing anything cryptographic related, but even shuffling. Like if you have an array and you need to do a proper shuffle, it can happen for multiple reasons, but it typically happens for mixedness, or if you look at electronic votation, digital votation systems and so on, you need to shuffle stuff in a secure way, and using math_rand would not be a good idea in these cases. So let's try again. How do we do to get a random integer smaller than 107? Well, we could take a random byte. It's a value between 0 and 255, and we could reduce it modulo 107, right? That seems quite intuitive. Well, bad news is that's introducing a bias. And we specifically call that kind of bias a modulo bias because it's related to the fact we've been using modulo to reduce a random value, and then it gets biased by the modulo. it's not the case if you're reducing a random value modulo power of 2, because then it's equivalent the modulo to just truncating the bytes. So if you have a byte string and you truncate it to, I don't know, 100 bits, then the 100 bits would still be random if you get a random byte string in the first place. And doing modulo with a power of 2 is the same as truncating a byte string. But let's see what a modulo bias looks like. So here is the modulo bias you would get if you were reducing a random byte with 107. So we can see the first 42 values from 0 to 41 are more likely, and almost a third, like almost 130% more likely, and that's quite bad. So that's definitely not what we want with when we want unbiased randomness. So how do we do to avoid such biases? Well, good question. And the answer is, in general, you can either do rejection sampling, which is something we'll see next. You can use a way bigger random value and reduce it modulo a small value. And when I say way bigger, I mean you need it to be maybe 100 or 128 bits bigger than the value you're reducing it to avoid the bias, because then the bias, as you know, is so small, it's negligible. And that's actually how some cryptographic schemes do. Like EDDSA is using 512 bits, random like bits, and reducing it to 253 bits, and that's unbiased then. And finally, there is a pretty cool divisionless method due to Lemur, which is pretty cool because it's super fast, because it's using no divisions, and divisions are super slow on a CPU, right? Well, for cryptographic PRNGs, the cryptographic PRNG is so slow anyway that it's not one division or two in the CPU code that will change a lot. So it's not going to be useful. So I just thought I would mention it here. So to avoid bias, we should be using CryptoRand. And we have a couple, very few APIs on CryptoRand. So first things first, we have a reader. So we can use the IO reader interfaces. Next, we have the funcInt interface. That's giving us a big int in a given range, which is, you know, pretty useful. Then with the prime function giving us a random prime, and then with the read function giving us bytes. And usually when you are doing cryptographic code, you're using bytes or big ints anyway. Well, maybe not anymore soon, because hopefully the RSA package won't be using big ints anymore, but that's, you know, for Go 1.20, hopefully. So also something I was told once was, hey, if I can't use the modulo, why can't I just use floats? I take my random value, it's from 0 to 255, I divide it by 255, I multiply it by the range I want to get, and that's it. I got a random value that's uniformly distributed, right? Well, not exactly. That's also going to be biased, but in very strange ways. So instead of having a heavy tail on the left side of the graph, you will get like strange spikes. And here is a playground link to see how the spikes look like. But it's basically because of the machine precision. It will be rounding stuff, you know, in a weird way. Also, it's prone to errors, because here, if you multiply by 107, you could still get 107. So you should be multiplying by 106 instead, and it might be counterintuitive depending what you do. It's not like other APIs whatsoever. Anyway, don't use flows. So rejection sampling. Rejection sampling is basically when you sample as a random value as long as you haven't found one which is in the range that you want. So with 107, I can take a range from 107 to 200, from 0 to 107, but I would be wasting a lot of possibilities. So what I can do is I can take the range from 0 to 214 instead. And that will work, because when you reduce random value in a given range modulo a divisor of that range, you're not biased. So that's rejection sampling for you. The problem with rejection sampling is if I were to sample a value that is maybe in the range from 0 to 130, that's pretty much in the middle of the range of a byte. And so I would be rejecting almost 50% of the values I'd be sampling. And that's not great for performances. So it's not necessarily the best way to do things, but at least it's a secure and easy way to do things, rejection sampling. The next option would be obviously to be using the crypto run package and be converting our big int into an int. That can work too. Usually you don't want to just get one integer when you do code that needs proper random values. So, but in case you're doing a shuffle or something, it could be useful. So that's for secret randomness. Great. We've seen how it works now. How about public or verifiable randomness? Strange things we've seen in the beginning, like if I want to do a lottery, how do I do it? The answer is there is no easy answer to that question. So it's not easy to get public verifiable randomness. There are some websites that are claiming to be using true random number generators that you can query to get, public random values, but that means you're trusting some website. It seems to be something like a threat model you might not want to have. Like the other option could be to use the NIST beacons, because NIST has released a random beacon project in 2013, and they launched a V2 in 2019. The problem is the NIST is well known for having tried to bias a random number generator. Maybe you remember the dual ECB issue we had a couple years back. So NIST might not be a third party you might want to trust, in general. So again, it's a bit So the question is obviously, can we do something simpler? Can we do something faster than what has been done in the past for public random values? And the answer that my team had was, we can do distributed randomness using open source software and provide a service that would be just like we have DNS or NTP servers. We provide free public verifiable randomness to anybody to use. And that was actually launched by in 2019 by a team of organizations, including Cloudflare, a couple universities, and so on. And so DRUN, it's called, is a software that is meant to be run by multiple nodes. And so the nice thing with that is that it's using threshold cryptography. So you don't need to trust any single node. You don't need to trust any single organization in the network. You just need to trust that there is never a threshold number of nodes that are malicious at the same time. And that is pretty nice, because if you have a set of organizations that are not related to each other and have no reason to, collude and be malicious together, then you can trust that the network will be producing proper values. And so DRUN was actually, written in Go in 2018, 2017, 2018 in a university in Switzerland. And it's using pretty cool stuff on the crypto side. So we've got distributed key generation, we got BL signatures, and so on. And it is checking all the boxes we might want to have for a public verifiable source of randomness. It's decentralized, so no single party or no central point of failure. It's unpredictable because you need to control the threshold of the network to be able to predict anything, which is quite difficult to do in practice. It is bias resistant, so it's unbiased and uniformly random values it's producing. And it's verifiable because you can verify it's been produced as it should by the group. And so the group of people running DRUN right now is made of Cloudflare, C Labs, a couple universities like UCL in London, EPFL in Lausanne, the University of Chile, but also companies like Kudelsky Security or Yolan and also a couple blockchain-related companies such as Ethereum Foundation or Protocol Labs. So it's a pretty diverse set of companies running nodes, and it's been running since 2020 with no single disruption. So it's been online 100% uptime since 2020, and we've currently produced almost 2 million. We've crossed the 2 million rounds in August. So we have a way to do public verifiable randomness, it seems. How about the entropy? You might be asking. Well, the pretty cool thing with DRUN is that every node can bring in their own entropy. So, for example, Cloudflare is using their lava lamps to seed their node, which is pretty cool. And to use it, it's fairly easy. We have HTTP endpoints with a REST API, so you can just query it in your browser. You can use curl, or we can also do it in Go, or in TypeScript, or in Rust. So the answer to the question, how do we do to get public verifiable randomness? Well, it depends on which service you want to use. If you want to use NIST services, then you'll need to look into that. But my answer to that question would be, hey, we've got this cool open source project that has been audited and has been running for 2 years, is backed by a lot of different organizations that have no reason to collude. So check it out. To get public verifiable randomness, you can just use the DRUN code base with a client package and the HTTP client package. And so here, for example, I take the chain hash of the network I'm interested in, which is the main network here. I take a HTTP endpoint. There are multiple of them, like Cloudflare is running a couple ones, Protocol Labs is running a couple ones. Anybody could run HTTP relay to provide a new endpoint if they want. And then we just need to wrap the HTTP client into a verifying client. So you can see here the client with chain hash option that is being passed. That's basically a way to build a root of trust, because the chain hash is containing a hash of the public key. So you cannot change the public key of the group. You can not tweak the group without it being detected if you provide the chain hash. So that's a way to get public verifiable randomness if you want to run a lottery. The other option would be to do it manually. So I'm going to walk through the different steps, and it's a bit more complicated. So the first thing you need to do is obviously to get a random beacon from the network. So you can do that with HTTP requests, or here I'm using the HTTP client. So here we can see a random round from yesterday. We got a random value. But how do we verify it, right? Because we might want to verify it. So the first thing we can do is verify it was properly derived, because the rounds are derived from the signatures. Because a nice property of a signature scheme in cryptography, for a cryptographic signature scheme to be secure, we require that a signature is indistinguishable from random. So here, DRUN is using the BLS signature scheme, and any signature produced by that scheme cannot be distinguished from a random value. So in theory, it's as good as a random value. So that's exactly what DRUN is doing. So we can hash the signature to get a random byte string out of it. And here we can check that if I hash the signature, I will get the same value as I got with the randomness. So first step is to check the derivation path. Okay, that works. Next, we're talking about signatures, so we will need to verify the signatures. And it's a bit more complicated, so it's why it's also nicer to directly have a verifying client API. But to verify the signature, we just need to instantiate the signature scheme. So here it would be BLS. We need to tell it what kind of scheme we're using. So here we are using BLS on the BLS 12381 curve. So that's what's happening at the top here. So we define a suit for BLS. We decode the public key. So we need to get the public key from the group. But that was generated in 2020, right? So it's public, anybody can look it up, and the public key of the whole group hasn't changed since, because it's using threshold cryptography. So whenever a new node joins, it's doing a distributed key generation, and it's doing a resharing of that public key using something a bit like Shamir secret sharing. And then we just need to construct the message we'll be verifying, because when you verify a signature, you need a public key, a message, and the signature. So here the message is the previous signature as well as the current round number we are verifying. So that's here being hashed again into a message. And then we just do the BLS verification of that message using the signature and the public key. And that worked. But then we just got a random byte string. So how do we do to do rejection sampling? For example, if we want to get a random integer between 0 and 107, like if I want to run my own lottery, and I say, okay, tomorrow at noon, I will be getting the public verifiable random beacon from DRUN, and that will be the winning ticket. I cannot use a 256 bit byte string. Like I cannot use a 256 bit string as a winning ticket, right? I need somehow to match it to the values we're interested in, and then that just means we need some kind of derivation. So we can take the random value and we can do a rejection sampling again by just maybe hashing it, as long as we don't get a new value that's matching, and that's what's being done here. So you can see we get the random value and we hash it. If the first byte is in the range we're interested in, it's good. Otherwise, we need to keep hashing it until we get a value that's in the right range. So it's exactly like we would do with the first rejection sampling, but here we are using a derivation from the public value. And that's it. So we get public verifiable randomness. A nice thing I thought I would mention is that using DRUN, you can also do a cool thing that is called time lock encryption, which seems a bit weird, but it's basically the notion that you can encrypt a message today that cannot be decrypted until Christmas, for example. And that's possible because every 30 seconds, DRUN is going to release a new random value with a BLS signature. And the BLS signature scheme is a pairing-based cryptographic scheme, and with pairings, we can do something called identity-based encryption. I won't bore you with all the math details, but basically that enables us to do time lock encryption. And the nice thing is we just released this year in August 2 libraries, one in in TypeScript and one in Go, as well as a demo website to do time lock encryption using DRUN. And yeah, I thought I would mention it because it's a practical thing. And yeah, finally, I figured I would mention, since I'm here and I know there are Google Cloud engineers and a lot of people maybe from Cloudflare and other companies, we're trying to grow the league because it's very useful to have a public verifiable random service, but it's only you can only put as much trust in the system as long as you trust that there is never a threshold number of nodes that are not compromised. And so the more diverse the set of organizations running the nodes is, the more trust we can put into the system. And it's not taking much to run DRUN. So the nice thing about it being open source is that if you don't trust the current league of entropy, you could also go ahead and build your own. So you could say, hey, I don't trust you, I want a crypto anarchist league, and you can go and run DRUN nodes on your own, providing public verifiable randomness to anybody that needs it, and run your own lotteries with it. And yeah, so if you want to join the league, talk to me or check our websites. Finally, also, I would like to mention we are hiring a lot of Go engineers within Protocol Labs because we are behind the IPFS file system, the interplanetary file system, which is entirely written in Go, as well as behind the libp2p, which is a library to do peer-to-peer in a secure fashion and easily, also in Go. So yeah, if you're looking for a job, you can also come and talk to me. And I see I still have a little bit of time, I think. So I have a few extra slides at the end in case you're watching this at home or reading the slide deck. So the threat model behind DRUN and the way we do public verifiable randomness is basically that You need to trust that the BLS signature scheme is secure. You need to trust that there is never a threshold number of nodes in the league that is compromised. And that's it. Well, almost, because BLS is not quantum safe, and currently there is no quantum resistant or post-quantum signature scheme that allows for threshold crypto systems. So if you're in academia and you're looking at a cool project, it might be worth looking into a threshold crypto system that are quantum resistant. That will be very useful for the League of Entropy and for DRUN in general. I'm not too worried. I don't consider quantum computers to be a threat for the next 5 to 10 years, maybe even 20. So, but in any case, it doesn't hurt to be ready, right? And yeah, that's it.